Hi again, this is Nick Marchuk. This is the second video of 3 where I'm designing a breakout board for the PIC32MX 170F256B. This breakout board is part of Advanced Mechatronics at Northwestern University in 2021. In the first video, I showed how to make a library of components in Eagle, and in this video, I'll show how to use those components to create a circuit diagram for the project at the end of this course. And then in the next video, we'll show laying out the actual copper wires. So I just finished making all of the components in my library. Some of these I stole from SparkFun and others I made from scratch. So the MCP 23017, this is our I/O expander, looks a lot like the PIC, the DIP format chip. We've got the DRV8835 H-bridge from Pololu. We've got push button, we've got a slide switch. We've got 5 pins for my snap programmer. I've got the ST7789 LCD screen. We have a 22 pin connector for the OV7670 FIFO camera board, and then resistors and capacitors and LEDs. Oh, and the Adafruit CP2104 Friend USB to UART converter. So we've got this mess of parts. Let's see how we can draw a schematic in Eagle. In the first video, I showed adding the PIC just as a demonstration. So I'm going to move that out of the way. And let's start by grabbing all of our power components down here. So we needed to add the library. We did that in the first video. I'll show again though. So I went to add a part, and you can go to Open Library Manager, and they'll show you all of the available libraries and the ones that you're using and the ones that the components of which you've actually populated into your current design. Sometimes I'll go through and I'll whack all the ones I don't plan on using on the in use, just because it gets annoying to scroll around, but we'll skip that right now. So instead I found the one that I made in available, and I clicked use, and now it shows up in the in use library. Called it ME433 2021. So when I go to add a part, I will find my library that I added all my parts in, ME433. And let's pretend that we have 2 power supplies. We're going to have a 5-volt power supply come in. Actually, where exactly does it come from? Let's take a step back. It's coming from the USB, the micro USB connector. So I'll grab my micro USB connector, and from that connector comes in a ground connection. So I'll grab my ground tag, and comes 5 volts from the V bus pin. So how do I connect the ground tag and the 5-volt tag to the connector where they come from? I grab this tool called the net tool. There's also a wire tool, or actually I call it the line tool. The line tool is for drawing lines, not for making electrical connections. All the electrical connections are made using the net tool. I'll select the net tool, and as you zoom in, and when you hover over something where an electrical connection can be made, you get a green circle. So I'll connect ground to ground. And I'll connect the bus to 5 volts. So when I plug the USB connector into a USB cable, the V bus pin will be energized at 5 volts. Anything now that gets touched to the 5-volt tag will also get 5 volts. Anything that's touching the ground tag will be connected to ground. Okay, we're going to have another power source. We're going to have a battery, a 4-pack of AA's. So that takes 2 wires. So I'm going to go to the Con2 library that I grabbed from SparkFun and grab the Con2 connector. And this is going to come in with a ground. And it's up to me right now to figure out which was which. So I'm going to put pin 1 to ground, and pin 2 is going to be, we're going to call it V+. That's the battery voltage. Those connections. And now this connector, which is just 2 holes right next to each other, I'm going to give the name battery, and I won't give it a value. Okay, so those two things are going to come into our board, and we're going to have a slide switch. And the slide switch will power our voltage regulator. So what does that look like? We're going to have a battery side of the voltage, a battery side of the button, and a 5-volt side. And so the 5-volt will come to the V bus pin, and battery side will go to the battery. And now the output, I want to go to the V in of the regulator. But I might also want it to go to other places too. So I'm actually just going to draw it out and double click to end. And then I'm going to grab this tag called label. I'm going to label that wire. Usually make it perpendicular like that. And then I'm going to name that wire V in. So just like we have a 5-volt tag and a ground tag and a V plus tag, we now have a tag called V in. So anywhere else I want either 5 volts or 6 volts to appear, I can make a net like I'll do here and give it a label. And then change that label's name to V in. And it says, do you mean to connect this wire to V in? I mean, yes. So that wire is connected to that wire. So I could have just drawn that green wire all the way connected, or I could give tags like this. So I need a ground for my regulator, and the regulator produces 3.3 volts. And we don't do anything with the shutdown pin. Okay, so far so good. So we have 2 ways to power our board to make 3.3 volts. Let's have a power indication LED. I'm going to choose an LED, and I also have to choose its size. We use 3mm LEDs in this class. And we have to put a resistor in series with the LED to limit the current. We're going to use 330. Now we have to choose the size of the resistor. So all the resistor schematics look the same, but each footprint looks different. So somehow you'd have to pick one of these. I like to use the 0207N when we're doing through. This is going to be powered by 3.2 volts and ground. Okay, so now we should have a light that's always on. I'm going to give the resistor a value of 330 and the LED a value of red. Remind myself that that should be a red power LED. So we've got our power stuff set up. Let's do, why don't we do the things that the PIC needs to work. So what does the PIC need? It needs the snap programmer. Here's my snap. We need a push button to reset. The push button needs a resistor. And since I already picked the right resistor, like the size there, I'm just going to copy that resistor. That's also for reset. And then I need 2.1 microfarad capacitors. I have to choose the right footprint for a capacitor. I think we'll go with this one. Capacitors, and then we need a 10 microfarad capacitor. Those are typically polarized, so I go from C pole. We want a through hole. We'll do this one. Okay, and then there's a bunch of connections to power and ground. I'll just go grab a bunch of power and ground connections. Okay. So my MCLR pin, I'm going to make a tag. CLR. CLR. And then we need to make the reset button. So from MCLR, we have a button to ground. Pull-up resistor. MCLR is to the pull-up button, ground. Okay, the VDD pin on the snap goes to 3.3 volts. Ground pin goes to ground. And then we have our two programming pins, PGD and PGC. And I've chose B0 and B1 for those, but we're gonna have to double up on those functions. So I'm gonna remember to give them their names, that full name. PGD, we're gonna call B0-PGD. And PGC is going to be B1-PGC. We'll make those connections. B0-PGD. B0-PGD. B1-PGC. Okay, so the PIC has the programmer attached. Need power on all the VDDs, grounds on all the VSSs, and then a capacitor from every VDD to ground. And VCAP gets our 10 microfarad to ground. AVDD power, capacitor, AVSS. Ground. The value, this one is 0.1 microfarads. 0.1 microfarads. 10 microfarads. VSS goes to ground. VDD is going to the capacitor, going to power. That one. Ground. VCAP. And the connection to ground. Oh, and there's a VSS there. Okay, so that looks like our minimum connections we need to get the PIC to work. We left off the crystal resonator because we're going to need all of the pins on the PIC to be able to talk to our camera. So we'll be running the PIC off of its internal regulator, internal RC resonator. Just out of curiosity, let's see what's happening as we add components on the board side. So this is the BRD file. Every time I added a component, it popped up down on the left here, and every time I made a net, it draws a yellow wire, a line from a pin, like MCLR, to where it's supposed to connect. If I do eyeball on that wire, it shows MCLR is going to pin 1 of the snap, and this push button, and a pull-up resistor. The pull-up resistor is on the back. So that's what's happening in the background. Every time we edit the schematic, it makes edits in the board. So once we're done with the schematic, we'll then be able to go and rearrange our board. Go back to the schematic, change the value of this pull-up. This is supposed to be 10K. Okay, so we've got our pick going. The next thing to do, let's add the friend board. We get our UART communication going. Adafruit CP21. 4. Has a ground connection. And then we're only using RX and TX. And again, we're going to be doubling up the functionality here. The RX pin, gave myself a note here. Is going to be B13. The TX pin is going to be B15. So this is a little different than in the video where we're using the USB UART converter. Keep your breadboard the way you've built it. It's only when we get to the final project will we move those pins around. And then we should probably remember to label B13 and B15 as we're using them. B15, B13, and I'll leave myself a note here with the text tool. That B15 is U1 TX. Typically, this is put in the symbols, the red text. And B13 is U1 RX. Okay, we'll double check that later. Okay, what else do we have? We're going to be talking to an LCD screen, the ST7789. And it needs to be powered by 3.3 volts on the VCC pin. And it gets a ground connection, ground pin, and then the clock, data, res, and DC pins will all be connected. So this display uses SPI communication plus 2 more wires. So it's not quite standard SPI. In this project, to be able to take advantage of the camera, which needs all these pins, we're not going to be able to use the LCD and the USB to UART connect adapter at the same time. So B13 and B15 will be shared with the LCD, and then you won't be able to use them both at the same time. Okay, the clock line is B14. The data line is B13, so this is shared. The res pin is going to be B15, that is shared. And the DC pin is going to be B12. So we're going to come back down here and mark off those pins that we're using. 12, 15, 13 is B14. And we're going to add some more notes. B14 is SCK1, that's the clock line for SPI1. $12. Going to the DC pin on the LCD. The 13 also going to be connected to STO1, the data out, and B15 is also going to be connected to res. So we'll either be using ARCS and TX or res and STO. Okay, so we've got communication slash display. Now we're going to need more pins. We'll save the camera for last. So let's connect the I/O fanning chip, the MCP23017. It has 1 power and 1 ground. And then typically wherever something has a power and ground connected to it, you should add a capacitor, a 0.1 microfarad capacitor. These boards, the little adapter boards that we've pre-bought, they usually have the capacitors online. This kind of dip chip doesn't have that built in, so let's be sure to at least give ourselves a spot to solder one in. We don't necessarily have to. So they call these a bypass capacitor. Power 3, ground, 1 microfarad capacitor. Okay, so this chip uses I2C communication. Using I2C, we can then communicate with it to make A0 through A7 and B0 through B7 input and output pins, and then we can use them to read buttons and turn on LEDs and do that kind of stuff. It has 2 data line connections, SCK and SDA, clock and data. These are fixed I2C pins. We're going to do a whole week on I2C and another week on SPI coming out very soon. So you don't have to know what this means yet, but we have to make these electrical connections to make sure the PIC can eventually talk to these. Okay, so SCK is going to SCL1, which is B8. And SDA going to SDA1, that's B9. And I2C is a little special in that it needs pull-up resistors, typically 10K. I'm going to give each of these its own unique pull-up resistor. And let's go find P8 and P9. And then we'll remind ourselves that B9 is going to be used as SDA1. B8 is going to be SCL1. Check. 8 is going to clock, 9 is going to data. Clock, 9 data, good. Okay, so now we can communicate with this I/O expander. We can chain many I/O expanders together to get even more I/O. So there are address pins, AD0, AD1, AD2. I'm going to set them all to ground so that this chip's address is 0. We don't want it to be constantly resetting, so we're going to set its reset pin high. We don't need this chip to be able to interrupt us, so we're going to ignore the interrupt pins. The NC pins means not connected, so they don't do anything. So the last thing we have is now we get 16 more I/O pins, and we're going to give one of them an LED and another one a push button. We'll put the LED on A0 and the push button maybe on B0. I'll just go copy those. LED gets it to 30. Push button on the pull-up resistor. Okay, so when we built this on a breadboard, we connected these directly to some pins. We need those pins for the camera, so instead we'll use I/O expander to get our user LED and user button back. And then user LED will be green. And I'll indicate that this button is user, and our other button is reset. Okay, now we'll need to be able to drive the motors, and we're going to use the I/O expander to drive our motors. So the H-bridge has 2 ground connections, has a VCC connection to 3.3 volts. The mode pin will be high so that we're in direction and speed mode. And the input voltage will be the voltage that we select with our push button, with our slide switch. And we called that the in. Okay, VM on the board, that's the voltage that is actually applied to the motor. So V in goes through a Schottky diode to make sure that if we plug in V in and ground backwards on this chip, we don't burn it out. So we're not going to use VM. Now we just have to select a pins for speed and direction. We'll call the motors A and B. We'll have A direction, A PWM, and then we'll have B direction and B PWM. Now, we actually don't have any PWM pins available because we're using all of the PWM pins to read from our camera. So we're just going to use digital pins from the I/O expander. And when we get to the project, we'll see exactly how hard it is to drive our, our motors with just on-off instead of PWM control. We'll make A1 on this fader. A2 will be APWM. 3 will be BDIR. A4 will be BPWM. And then we have to be able to plug our motors in. So we'll use two 2-pin connections, motor A and motor B. Okay, so that's our H-bridge connected to 2 motors, getting its instructions from the I/O expander and power from our slide switch. Take a peek over at all the components that we'll be organizing later on and all those wires that we'll have to make on the board layout. That'll be fun. And we're almost done. So the last thing we have to do is add the camera module. So cameras are notoriously hard to work with because there's just so much data that comes out so fast. This camera module has a FIFO memory chip built in. That'll make it easier for us to slow down the rate of data, but the data still comes out as a parallel port. So from D0 to D7, that's the data. Every byte will read a bit from 8 pins at a time. And then there are lots more pins that control the flow of the data, as well as power and ground. So let's go grab a power and a ground. 3.3 volts, ground. And not all of these pins are needed. We're going to go over them in detail later on. I'll just tell you which pins I've selected on the pick to be able to communicate with the memory chip, and hopefully this works later on. So SIOC, it's kind of like a I2C pin, but not quite I2C. So we're not going to share the I2C bus. We're going to bit bang this. So SIOC, that's going to go to B6 on the pick. And SIOD going to go to B7. And because this is like I2C, they need pull-up resistors. And I'm slightly worried that 10K isn't a good pull-up resistor, so we're actually going to use a specific value of 4.7K. Because that's what the data sheet specifically asks for. And online, some people said 10K didn't always work. So 4.7K for those pull-up resistors. Grab B7. leave ourselves a note for what we're doing. Seven is SI B. B6 is SIOC. So one's the clock and one's the data. Okay, so that is used to initialize the camera and tell it what kind of resolution and color and all that kind of stuff for setup. Then we've got all the data to come out. So let's grab our data pins. 0, D1, D2, 3, D4, 5, D6, and D7. Now this actually looks like a pretty good candidate to have used the I/O expander to read this data, because the I/O expander could have essentially turned this parallel data port into a serial data port. But it's very slow, the I2C communication. I opted not to do that here at the sacrifice of losing lots of pins on the PIC. So how we're going to read 8 bits at a time. Normally we could do that by saying like port A bits or port B bits. So we'll try to organize these so that some of these are on A and some of these are on B, and they're easy and fast to read. We want to maximize the read speed from the camera. We're going to use A0, A1, A2, and A3. We got A4 too. Yep. So those will be the low bits. A0 is going to be D0. A1 is going to be D1. A2 is going to be D2. And A3 is going to be D3. So we got the first 4 bits. And then we'll use the low B pins to grab the others. So B2 and B3. Going to be our D6 and D7. Okay, and B0 PGD now going to be PGD D4 and PGD D5. We're also doubling up over here. D4, D5. So hopefully the programmer and the camera don't fight each other. So this is going to be P0, PGD, and D4. This is going to be P1, PGC, D5. This one didn't give me that ding, because I must not have typed it in right. B0, PG, D4. Okay, that's all the data. Then the other important pins that come out. VSY tells us that we have a new picture. We get a pulse per picture there. We need RCA, WR, and W reset, and R reset. What do we have here? B4 and A4, 5, B10. So B4 is going to be BSY. A4 going to be RCK. BSY. Five is going to be WR. B10 going to be R reset. And B11. Spin on the pick. W reset. 1, 2, 4, 5. 1, 2, 3, 4, 5. Okay, and then we don't want this thing to be resetting itself all the time, so look up OE 3.3 volts and the reset pin 3.3 volts. Just a minute. Okay, so OE power. STR doesn't go anywhere. That's a strobe pin for doing LEDs. Power down, that has an internal. We don't have to deal with that. And HREF, that's a pulse per new line of camera images, but we're not going to use that here. We might want to use them in the future though, so I'm going to add a single hole next to the pins that we're not using, just in case. Kind of like debug points. Okay, so look at that. The pick, every pin is used. Some of them are used twice. Camera's hooked up, H-bridge is hooked up, the I/O expander hooked up, but some pins haven't been used. So all of those unused pins, we'll give them holes, just in case we change our mind later and want to use them. Okay, we've got our LCD screen and the USB to UART. We've got all our power. We've got the programmer. Okay, so that was designing a schematic for the PIC32 circuit we'll be doing at the end of the class, at the end of the course. The next step is going to be arranging all of the components onto the printed circuit board, connecting all the pins with wire, and then putting labels on and generating Gerber files. So I'll see you in video 3.